Right, we're going to try one more problem. Here we're asked to find the structures of A and B, and we're given two possible reactions that A undergoes. The first is a hydrogenation reaction in which A forms this alkane that has two branches. I can tell that A must be an alkene because it reacts with hydrogen and with a platinum catalyst, but also because its formula is unsaturated. It doesn't follow this pattern CN H2n plus 2, because if it did, it would have the formula C10H22. I can tell that it has 6 hydrogen fewer than that. That indicates that this molecule must have 3 double bonds, or 1 or more rings could be present as well. Okay, so that could be the result of 3 rings, 3 double bonds, 2 rings and 1 double bond, so on. However, I can see that this product has no rings, okay? So this must be the result of 3 double bonds. Okay, so let's look at the second clue that we're given. We see that A undergoes ozonolysis followed by dimethyl sulfide to form 2 moles of formaldehyde, 1 mole of our ketone here, propanone, and B, which has 5 carbon and 3 oxygen. Right? So let's see what we can figure out working backwards. When I see that it forms 2 moles of formaldehyde, that indicates to me that our double bond must have 2 terminal carbons on the ends of 2 of the double bonds. In other words, somewhere in the molecule, I've got this. In fact, I've got 2 of those. Okay, so I'm going to look back at my initial molecule, or my hydrogenated version of A. I want to look for possible locations where a double bond could be on a terminal carbon. And I see that I have 4 terminal carbons in this molecule. Okay, so 2 of those terminal carbons are going to have double bonds attached to them, and the other 2 won't. So we need to figure out which 2 of those are. Okay, so let's look at our next clue. I have a double bond attached to a kind of like a isopropyl group, right? A propane. So I'm going to look for something like this in the molecule. Okay, we've got a double bond attached to that for that fishtail isopropyl group. So when I look here at this molecule, I only see one potential isopropyl group. That's close, but not quite. Okay, so this tells me there must be a double bond attaching that that propyl group on the initial A molecule. What I'm going to do is I'm just going to copy this molecule of A so that I can mark it up when I figure out where double bonds should be. Okay, and I know there's going to be a double bond here, right? Okay, so remember I have 2 other double bonds on terminal carbons. I only have 2 more terminal carbons left now that I figured out the double bond here belongs to that second product, the formaldehyde, or the propanone. Okay, so let's see if this works. We put double bonds here, double bond here. Okay, if I were just working backwards, if I were to cleave these, this would indeed give me my propanone. This would give me my formaldehydes. Okay, so what would I be left with? What would B be? Well, hopefully it has 5 carbons because that's what the problem says it should have. So it would have an aldehyde here, have a ketone group here, and it would have an aldehyde here. All I did was I just redrew this backbone with those double bonded oxygens. Okay, and I always like to just double check by counting my atoms. 1, 2, 3, 4, 5 carbons. Okay, 1, 2, 3, 4, 5, 6 hydrogens and 3 oxygens. So this looks pretty convincing to me that this is indeed B. which would make this a correct form of A. Okay, a little marked up, but we could redraw it. Okay. So cleaner version of A. Okay, so again, hopefully that helped you kind of see how we could work backwards. And the key is looking at those products of the ozonolysis to identify where the double bonds could be. All right, if you have any questions, please let me know on Google Classroom or via email. Have a good one.